You please proceed, sir.
Should I start now?
Yeah, how many numbers are there? Yeah, I think you please wait for 5 more minutes because people are coming in.
Okay, madam. Okay, fine.
Okay, sir. Okay, sir.
కాదు మీరంతా మొత్తం అన్ని ట్రైన్ చేసుకొని ఎలా ఉండాలంతా చెప్పుకున్నప్పుడు ఇప్పుడు కనీసం వేడి దగ్గర కూడా లేదు కనపడకుండా హస్తాంతరం ఇంకొక డాక్టరేట్ ఇస్తాము మీరు డాక్టరేట్తో పాటు చేయించండి డాక్టరేట్ రాత్రి 1 గంట నుంచి 3:40 వరకు అన్నీ చెప్పుకొని అన్నీ చేసుకుని ఇప్పుడు ఇంకొక నేర్చుకుంటారు. అది కూడా ఇంకొకటి ఉంటుంది మీ వాళ్ళు కూడా ఏంటంటే ఎక్కడో లింకులు ఉంటాయి ఏంటి బయట కనపడదు కానీ
Okay, so now we can start.
Yes, sir.
Yes.
Sir,
So, yes.
start. We can start, sir. Slowly people are joining.
Yes, yes. So, basically, in today's hands-on session, today's session is basically hands-on session for the design of terahertz components. So, terahertz components, I discussed terahertz dielectric resonator antenna, cylindrical DRA, and rectangular DRA also. So, using CST Design Studio, first we will design 1 terahertz antenna, and with me you also design. CST, you can install the student version, it is free, and you can design. You can learn how to do how to design the terahertz antenna for terahertz communication in CST. So for that, my PhD student has also joined. So he will guide step by step. I will be also joining, designing the antenna. You also do the hands-on training. Terahertz antenna already I explained. Gigahertz antenna also I explained. So Yakub, you can share your screen. CST screen you can share.
Sir, no, sir. This one is presentation only, sir.
He will share. No?
Yes, sir.
Sir, my voice is clear, sir?
It is clear now. You can share the CST screen.
Okay, sir.
Yes, good, good. It is visible.
Okay, sir. Screen is visible, sir. Okay, sir.
So in the project template, what should we choose?
Direct I explain, sir, now?
I mean, starting how to open CST.
Okay, sir.
From
Okay.
there you explain.
Okay, sir. Okay, sir. So, good afternoon, all of you. Myself, Bhanat Yakub. I am a PhD student under Dr. Amarjit Kumar sir from NIT Warangal. So, today I will explain to how to design antenna design in CS by using of CST Microwave Studio. So, in terahertz, we can implement the one antenna design, and how to we can simulate, how to we can give the port excitations, all things I can explain clearly step by step. So before I will going to the design, how to open the CST Microwave Studio. Uh, the starting, so all of you can, your laptop or your desktop, you can use your student version CST Microwave Studio. It is available in Google. So all of you install student version CST Microwave Studio. I am using the CST Microwave Studio as a licensed version. So after the installation CST Microwave Studio,
What is your
the,
version, Yakub? CST?
the mine is 2018, sir.
Okay, so here we have CST Studio Suite 2024.
Yes, sir. Yes, sir. In student version available, sir. The new version also.
Yes, yes, you can.
So the after the CST Micro Studio installations, go to the file. There is the new and recent. The block will be available. So click on the recent and new and recent file. Click on that one. Here the new project from template. The new project, new template will be shown. So click on the new template. So here the lot of options it will be shown here. The and RF optical, ED and electronics, EMC and EMI, and this is the parametric dynamics, statistics and low frequency. All things will be visible. So just to select the your what you are area, that option will can choose here. So today we are designing terahertz antenna. So that's why that purpose we are choosing this one, millimeter and RF. Just mouse drag on that millimeter and click that option only. So it will be shown little bit option. Some option will be shown. The antennas, circuit components, radars, cross section, biomedical, optical application, and periodic structure. So after the clicking the millimeter and RF and optical, it will be shown lot of options here. The antennas, what we are designing the antennas, the RF circuit components, and the radar cross sections, and for the biomedical applications related things will be shown here, and the optical applications also shown here, and the periodic structures for this option also shown here. Periodic structure, in periodic structure we can design the biosensor, all things we can design in this periodic structure. So today we are designing, go for to the antennas. So select the option, click on the antennas. So select the antennas, go to the next. It will be shown lot of option here. The different antennas are there in our RF side. And this waveguide horn antennas, planar, wire antennas, phased array, unit cell antennas, the mobile phone integrated antennas, reflector antennas, dielectric resonator antennas, RFID. The number of antennas is there in our RF side. So today I am showing the design on dielectric resonator antenna. By using the dielectric resonator, we can the design on antenna in terahertz frequency. So that purpose I am choosing the dielectric resonator. So just select that one, dielectric resonator. It is visible. The screen is visible or not?
Yes, it is visible.
Visible.
So lot of antenna side is there. The waveguide horn antennas, the
Hello?
planar antennas, that in this one patch antennas, slat antennas, wired antennas,
ఎంత
reflector
ఇప్పుడు?
antennas, mobile phone integrated antennas. So today we are going to the
ఎక్కడికి వెళ్ళి?
designing the dielectric resonator antenna. So that purpose I selected that dielectric
నేను
resonator.
25
After the selecting, go to the next.
259.
So after the selecting, it will be shown the two domains, time domain and frequency domain. So we are designing antenna in time domain. The frequency domain, it is used on that
ఈ 108
basically in
ఫస్ట్ ఫ్లోర్ లో
biosensors purpose. In antenna designing, you can select the time domain here. So the time domain you can select and click on the next. So after that time domain, it will be shown the lot of options here. The what dimensions you are designing for your antenna and which frequency you can design and the what time you can selected, the temperature, voltage, all option will be shown here. So basically what you are designing antenna, that dimensions value you can give here. So today we are designing the antenna in terahertz frequency. So dimensions you can take as a micrometers. If you want the antenna in gigahertz frequency, you can select the millimeter. So today we are designing terahertz. Terahertz purpose, you can take the values as a micrometer. And the frequency, if you are going to the frequency, it will be lot of option will be shown here: kilohertz, megahertz, gigahertz, terahertz. So today we are designing in terahertz frequency. So you can select the terahertz frequency. If you want the designing gigahertz frequency, you can select in this one, gigahertz. So today's antenna in terahertz frequency, the terahertz frequency you can select. The time is same as it is as nanosecond. The temperature Kelvin, the other option, you don't change anything.
In my case, it is showing the degree Celsius temperature.
So select Kelvin, sir.
Okay, Kelvin, fine.
Okay, sir. So after that, given the all dimensions, the particular frequencies and the time, then go to the next. So here the frequency, what frequency we are designing for your antenna, that frequency values you can give here. So in terahertz frequency, normally in this generation, in this normal RF side, the terahertz is the very high frequency. All research is going on. The frequency range is 0.1 to 10 terahertz. So in this range, the normal research is going in this terahertz frequency. So today we are today the same what we are using in the actual frequency range. That frequency range I given here. Frequencies minimum is 0.1. The maximum frequency is 10. So 0.1 to 10 maximum frequency terahertz frequency is given for this particular antenna design. So it is clear the how to we can give the terahertz frequency ranges given to the particular antennas. The 0.1 to 10. So I given here. After the given the frequency range, go to the next.
The monitors you didn't choose electric field or magnetic field, these things, far field.
That is the one thing, sir. After the
Later
simulation,
on we can add, okay.
after the simulation point, far field, electric field, and H field, far field, all things we can
Right.
step by step. I will show to the audience, sir, how to the electric field and H field we can
We can
select.
add later also field monitors.
Oh, yes, sir. Yes, sir. So after the range selection of the particular frequency, go to the next. So here you can see the create project template. In starting to ending purpose, the solver we are taking chosen as the time domain, and the units we are given as the micrometer for terahertz frequency. The frequency also here shown here, terahertz frequency. Time is nanosecond. The temperature is Kelvin, and also frequencies we are given for this particular design as a 0.1 terahertz to 10 terahertz. So all option what we are given, all things will be shown here. It is clearly, if you any changes, you can go to the back and change your dimensions values. It is clear? Hello.
Yes, Yakub.
Yes, sir. Yes,
Okay.
clear.
Okay, okay. Sir. So just click on the finish. It will be open the new project file in CST. So it is loading. I think all of you open your CST Micro Studio, and the screen also what I open all.
It is yes, opened.
Okay, so this is the CST Microwave workspace. In this workspace, we are designing the what we are antennas in terahertz frequency. So before the designing part, so what I design, which antenna today I will design and how to works, all things I will shown the basic diagrams. So before that simulation designing part, I will show to the which antenna we are designing today's session. So you can see the visible, sir, this figures.
Visual.
Yes, please will.
So this is the normal DRA, dielectric resonator antenna. The upper side is the CDRA, cylindrical dielectric resonator. The bottom is the yellow color one is the ground metal layer. The sky blue color is the substrate layer as a polymer lossy. This is the basic structure of this today's simulation. What we are designing of that antenna. So this is the side view. And the bottom you can see one microstrip feed line with the pink color. This is the microstrip feed line we are using in this particular antenna designing. So this is the bottom view, and this is the front view. What we are designing today's session. This is the front view of the particular antenna design, and this is the side view, and this is the wide view. So you can see the clearly in this one, in this antenna designing, we are using aperture coupled by using of microstrip field line, bottom microstrip field line, and one of the cross slot also we are using. On the cross slot we are kept the one DRA. So it is visible clearly now, all of you.
Yes, visible, sir.
Yes. So this simple design in terahertz frequency, how to we can design and how to simulate, and how to we can identify the return loss of that particular antenna design, and how to we can see the particular gain for this antenna, and we can see the radiation deficiency and axial ratio, how to we can identify, and also for SAR saying that far field, electric field and magnetic field, how to we can see for this particular design. This all things I will explain clearly step by step. This is the our normal antenna designing. Today what I designing this antenna, simple antenna designing, basic view I will shown here. So this design today we are going for design and simulated in CST Microwave Studio. So that purpose, so normally in antenna designing, the two layers in this one, bottom layer is substrate layer, and upper layer is the yellow color one is the ground metal layer. Two layers are designed here, and the top of that ground metal layer one cross slot will be shown. The cross slot is there, and cross slot we make it as a DRA, and the bottom is the microstrip feed line. For this design, I will explain in CST Microwave Studio. For that purpose, first the sky blue color one you can select the substrate metal. So that for substrate material purpose, in file in CS, after the open the CST microwave workspace, it will be shown lot of option: home, modeling, simulation, post processing, view. So going to the home, the lot of option is the simulations option, parametric sweep, and all things will be shown here. For the create the substrate material purpose, for new material or any material for the designing purpose, so go to the modeling option. Here in modeling, it will be shown lot of options: brick, the sphere, cone, torus, and cylinder. The options are lot of options shown in modeling. So in our case, the antenna, the starting material is substrate material. For that, the substrate material dimensions has a 60 micrometer and 60 micrometer as a square wave brick. So that purpose, I am selecting that this brick. After the selecting the brick, just to click on the escape in keyboard. Just to click the escape button, it will be automatically shown. It is clear?
Yes, Yakub, continue.
Clear.
Okay. After the escape button, automatically what we are selecting, the brick or cylinder or cone, anything. After the selecting, just to click on the escape button, it will be shown the dimension, particular dimensions, the brick dimensions. It will be asked. In this, you can give the what material, which substrate layer or ground metal layer or with how much dimensions we can design. All things you can give values here. So in our design, already I shown sky blue color one, the starting substrate layer. So today, so now I am designing the substrate layer here. So name you can give as a here, for particular brick name as a, the name you can give substrate. The substrate we are designing in starting. So substrate material name you can write as a substrate. The name you can give as a substrate. The X minimum, Y minimum, the particular brick dimension is asking the width and length and height of that particular substrate material. So X minimum you can give as a minus W/2, the width of that particular brick. X maximum you can give as a W/2, width of the particular brick. And the Y minimum you can give as a minus L/2, and the Y maximum you can give as a L/2. And Z minimum you can keep it as a 0. The starting material we are designing, substrate material, the thickness of the starting material is going for to the thickness of, you can give as a thickness of the feed, thickness of the substrate as a TS. The starting material, the thickness material, the particular dimensions. So here the material you can choose for this particular brick. The material we can selecting for this brick as a polymer lossy.
The
So
silica is there or not in material library?
it will be silicon, sir, SiO2, sir.
SiO2 is available, or we have to give the property?
Yes, sir. We can see in the material library side, it will be
You are
not shown.
taking polymer lossy, huh?
Polymer loss. We are taking the polymer lossy.
But is
So-
it there, polymer?
Yes, sir. It will be there, sir. Click on the load from material library. Just here, material in search in material. Just to give that particular material name as a polymoid. Just give the name, sir. Polymer loss. It will be shown, sir. Fourth
Yes, yes,
option.
it is. You can load it.
Yes, yes. After the selecting, just click on the load. And after the selecting the material, click on the preview. It will be ask the dimension values of particular brick. So width we are given as a 60 micrometer. The length also same as it is 60 micrometer. And also thickness for this particular material we are going 1.50. You can give as a 1.50 micrometer with height. After the given the all dimensions value, just click on the OK. So I will change the material is created here, substrate material, but it is not visible clearly. So that purpose I am just this material color I will be change and show to that what we are designing this substrate material. For that purpose, select the substrate material, go to the change and material color section. Here the material color you can
What you clicked assign material and color.
yes sir, yes sir.
And
So
after that, what you have done? Overwrite material color.
sir, go to the change and material color, sir. Just click on that one.
Yes, yes, it is done.
Okay, sir. Here the in the already in this design we are selected polymer lossy. If you want to change the material, we can change from here on also. Here the option will be also shown. Load from material library. In this, click on that one and change the particular what you want material. That material also we can change from here, and the color will be changed from this option. So it is clear, the visible clearly the substrate material, the sky blue one color.
Yes, sir. Visible. It is.
Okay, okay, sir. So that working place space, I will modify some options in this view. Working place I removed and boundary box and access for clearly visible purpose. I removed that things. So
What you
the
removed? Working plane.
yes sir,
Okay,
in this view working plane, if you click on the double one, it will be removed, sir. And also boundary box access, all things are there. For clear visible purpose, I remove all things, hide it. So the bottom, the first thing, the substrate material, sky blue color one is we are designed here. So after then, we go for to the design microstrip feed line on the top, in the bottom of the substrate material. You can design the microstrip feed line. For the feed line purpose, designing the feed line purpose, go to the modeling and take the another brick. The microstrip feed line purpose, designing purpose, just to go to the modeling and click the brick. Just click the escape button. Here the particular brick dimensions will be asked. So here the name you can give as a feed line for this particular design. Here asking to the x minimum, x maximum, y minimum, y maximum, z minimum and z maximum. The x minimum for this particular field line. Here the normally in antenna designings in gigahertz or terahertz frequency up to 3 micrometer or 3 millimeter width we can basically use in any design. So up to 3 is okay. After the 3 is not possible for the good results. The 3 is the width is the 3 micrometer or 3 millimeter is the good results we can see in that particular dimensions value. So in our field line, the width you can give as a up to minus 1.25 to 1.2, 2.50 width we are given here. X minimum 1.25. The X maximum you can give directly. You can width values you can give 1.25. Length we are in this design we are using for 35 micrometers for that purpose. By minimum you can give the 5 micrometers and y maximum is the give as a minus 30, and the Z minimum is a 0, and Z maximum you can give as a thickness of feed.
5 and minus 30 you have given, no? Y min and Y max.
Yes, sir. Y minimum is the 5, sir. Y maximum given as a minus 30 for this particular length value, feed length value. The dimension is we are giving minus 1.25 to 2.50 width, and the length is 35 micrometer. And the particular feed line, the material will be, we can select. For that purpose, go to the load from material library. For this particular feed line, we can give in for this feed line material as a silver. So just in material, you can search button, just type the name as silver. It will be shown automatically here silver. Just select this one, silver material. In terahertz frequency, feed lines are for particular feed lines, silver material and gold materials are using. For with this particular antenna designing, in this designing for the material of that feed line, silver we are using. So that purpose we are going to select the silver material here. So just the give search, in search button you can give the silver material name. Just select the silver material and click on the load. After then go to the preview. Just click the preview. It will be asked the thickness of feed. In thickness of feed we can give 0.035. The thickness feed in gigahertz frequency or terahertz frequency, the constant thickness is there 0.035. That thickness you can use in any applications for feed line purpose. In gigahertz applications or terahertz applications, the thickness value you can give as a feed line is 0.00035. So after then given the thickness value, just click on the OK.
Actually, for microwave, we are using 35 micron.
Yes, sir.
So here it is 35 millimeter. Actually, this is TF. TF means thickness of the feed. Na?
Yes, sir. Yes, sir.
So thickness of the conductor is 18 micron or 35 micron. Here also you have taken 35 nanometer because it is 0.035 micron. Correct or no?
Yes, sir.
So it will be 35 nanometer
Yes.
for terahertz.
Yes.
And for gigahertz it is 35 micron.
Micron, sir. So you can see that bottom layer, the yellow color one is the feed line we are designing here. It is visible clearly.
No,
bottom-
actually,
Visible, sir.
Yakub, yes, now it is visible.
Sir, visible, sir.
Now it is visible.
So the bottom feed line is over. The upper substrate material designing point is over. Now we can, on top of the substrate layer, one ground material we can design with the
So
same.
can we change the color? It is here yellow color for the feed.
We can change, sir. For that purpose,
But
select
it
the
is fine, huh? Yellow is fine.
yellow. The ground material also we can design the yellow color, sir. So little bit we can change the material color. For that purpose, go to the select and select the pink color. It is visible clearly.
Yes.
Okay. So you can see here the same structure we are designing here, the bottom layer. The pink color one, the microstrip feed line, another one is the sky blue one is the substrate layer. So bottom layer and substrate layer design is complete. Now we can design the ground material layer on top of the substrate layer with the same dimensions. So what we are taking for that substrate material, the same dimensions you can take for that ground material. So that purpose. So before going to the ground material designing, little bit change in substrate material thickness. So go to the substrate in this define and brick. Here the bottom layer is added. The thickness of feed is added. That you can give as a Z minimum. Here the thickness of the microstrip feed layer thickness is added here, Z maximum, thickness of feed plus, and thickness of substrate layer.
So
So-
TF to TF plus TS.
Yes, sir. Z minimum
You are modifying this.
modifying it, sir. The bottom layer is added in top of the substrate layer, sir. So
But
that
you are modifying the brick, na? That one.
bricks, sir. It will be added, sir. The Z maximum you can give here as a TF plus TS, thickness of feed plus thickness of substrate. It will be added automatically. You can see. Okay. So we can go for design the ground material layer on top of the substrate layer. So that purpose, you go to the modeling, select the another brick, click on the escape button. Here name you can give as a ground material we are designing, no? So that material name you can give as a ground material. So name we are given as a here ground material. The X minimum, X maximum asking here for that particular brick ground material. So what we are given that particular substrate dimensions values, same values you can give. Same square material we are designing top of that substrate layer. Same dimensions values you give for this particular ground material. So in that substrate material we are given as that X minimum is minus W2. That same dimensions values you can give here, minus W2, and X maximum given as a W by 2, Y minimum given for minus L by 2, and Y maximum L by 2. The dimensions values already we are given to that substrate material. Same thing we are designing here for this ground material. Here Z minimum. So in Z minimum, thickness of feed plus thickness of substrate material TS. This is the minimum thickness. In Z maximum, same thing will be, you can give thickness of feed plus thickness of substrate, and plus we are go for designing ground material. That thickness you can add here, Z maximum. For that purpose, you can give the thickness of ground material as a TG. It is clear? Okay. The thickness, the bottom layer Z minimum, already we are designed thickness of feed. That is already pink color. I can show now. The thickness of feed, pink color one, and the thickness of substrate material is the sky blue color substrate layer. So we are going to design the ground material. That thickness also added on top of the substrate layer. So that purpose we are given the added TG here. So you can, after the TG, you can select the particular ground material. So ground material we are chosen for this particular design as a silver. So go to the load and material library. Here you can material give as a silver. In terahertz frequency, the ground materials basically we can use a silver material or gold. In this particular antenna designing, we are choosing for that silver material. So select the silver and load it. So after the selecting the material, just click on the preview. So here already the W and length values we are given for the substrate layer. For the width and length values not asking here. Only the new material values asking, the thickness of the G, that dimensions value added asking here. So thickness of the ground you can give here as a 0.035. The particular ground material as a give as a 0.035. Just click on the OK. Just preview and OK. It is shown clearly. It is visible.
Yes, sir, visible.
Okay, sir. The sky blue one is the substrate layer, On top of that substrate material, we are design the ground material with the thickness of 0.035, and the bottom we are design the microstrip feed line. So here the microstrip material we can change little bit in design. Some variation is there. The material we change as a gold. So just change the material for that feed line, gold material. Okay. So this is the three layers we are design completed. You can see the basic diagram here. So you can see here the bottom microstrip feed line with the pink color is over, and the two layers of that design, the substrate layer, the sky blue color one with thickness of 1.50 micrometer, and the top of the substrate layer we are design the ground material layer with thickness of 0.035. So we now after the completion of this two layer design, you go and design the cross lot. Cross lot we can design on ground material for that the that excitation purpose. The whole we can make it as a cross lot. On that cross lot we can design the CDRA, cylindrical DRA, dielectric resonator. So this now after the ground material designing, we can start the cross slot and make it on ground layer. So for that cross slot, you can go to the modeling, select the brick. In here brick, the for the particular cross slot, just click the escape button. So here the name you can give as particular brick is cross slot. So we are designing cross slot. That name you can give here. The x minimum, the width and length, all dimensions value asking for that particular cross slot. X minimum you can give as a minus SW slot width, and x maximum you can give as a slot width. Y minimum you can give as name here slot length. Y maximum you can give as a SL slot length, and the Z minimum TF plus TS, TF plus TS plus TG. On top of the ground material, we are making the design that cross slot. So the thickness you can add it here. The material same what we are selecting the ground material silver you can give here. You select the silver material. With the silver material, you can make it that particular cross slot. Just click on the preview. Here the slot width is asking 1.25 dimensions where you can give, and the slot length you can give as a 10 micrometer. Just click on the preview. Okay. One rectangular box is shown on top of the ground material layer. It is visible or not? Hello.
Sir, visible, sir.
Okay, sir. Okay, sir. So with the rectangular brick, particular rectangular brick, 1 minute. Sir, Nageshwar, sir. Hello. Sir,
Sir.
just 2 minutes, sir. Sir is calling, sir.
Okay, sir.
Sir. He is working, sir. Session is going on. Okay, sir. Sure, sir. Hello, sir. Naishwara, sir.
Yes, sir.
Sir is left, sir. The network issues are there. Sir
Okay.
left, sir. Just now
Okay,
informed
sir.
to me. So we can proceed, sir.
Yes, sir. You can proceed, sir.
So the rectangular brick we are design here. For this particular rectangular brick, we can make it that cross slot. So that purpose, that you select the cross slot, go to the transform. Here in modeling transform, in the transform option will be there. Just to click on the translate. Here just to the particular cross slot purpose, the rectangular brick, just copy and rotate with a 45 degrees angle. We are making the cross slot with particular dimensions as a 1.25 width and 10 micrometer length. We are by using of two bricks, we are making the cross slot. So just apply and OK. So I will show the visible, it will be clear now. So one cross slot we are copy and rotate it with the 45 degrees. So select the another cross slot, the go to the transform and click on the translate option. Here the particular what we are selecting the brick, the that brick will be select, and this brick you can rotate with the angle of 315 degrees. So it is visible now clearly the particular cross slot how we are making designing with using of two bricks. Okay, it is visible or not?
Yes, visible, sir. Visible.
Okay, okay. So I will show. The cross slot is the shape is, it is visible clearly now, the cross slot with by using of two bricks. So the already the shape is visible now. You can make it two cross slot. You can add it for that for that purpose. Select the what we want the added the material. Select the cross slot one and cross slot. Select this one and just control shift the control button. You can select the cross slot bricks. Go to the modeling. Here one option will be there, boolean option will be shown here. Just go to that boolean option, just add the particular material values what we are selecting, the particular bricks, that bricks you can add here, it will be automatically added. So it is visible or not?
Sir, visible, sir.
Okay, okay, sir. The cross slot we are make it as same what I designed in this basic design shown in starting. How to we can make it in cross slot for particular design. You can see here the wiring view, the design we are implemented here. So this cross slot we can make it as a hole, make it at a hole on the top of the ground material layer for that excitation purpose. So that purpose you can select the cross slot, go to the no, we select the on top of the ground material, that particular cross slot we can make it as a hole for that antenna excitation purpose. That purpose you can go to the ground material, just go to the ground material, go to the boolean and subtract subtract the cross slot material, cross slot shaped. Just select the cross slot, just click on enter. It will be uh, shape as a whole as a cross slot on top of the ground material layer. It is the design is clearly visible that in top of the ground material layer you can see the bottom layer is shown here clearly, the substrate material layer, sky blue one. The so we make it as a particular cross shaped hole on top of the ground material layer. You can see the bottom layer substrate layer is also visible clearly with this particular shaped hole. It is visible or not?
Visible, sir.
Okay. So you can see here the basic diagram. The what we are designed up to here, that bottom microstrip field line is completed, two layers substrate layer and ground metal layer, and the top of the ground material layer we are designed that one cross slot also we are implemented. On the cross slot we can go for design the CDRA, particular cylindrical dielectric resonator antenna we can design, and how to we can give the port excitation, how to we can simulate, how to we can see the particular results for this design, how to we can see that particular far field electric field magnetic field results. And also we can see that in the top of the DRA material we can design the graphene by using the graphene material, how to the particular results it will be tunability, all things we can see now further steps. So before that going to the design, the cross slot is there. On the cross slot we can implement the one cylindrical dielectric resonator we can design. For that purpose, go to the modeling. Here the last option cylinder option will be there. Just click on the cylinder, just click escape. Here name you can give as a DRA material as a CDRA, cylindrical dielectric resonator antenna. A particular cylinder dimensions value asking here: outer radius, inner radius, x center, y center, z minimum, z maximum, and different segments are asking. The material also there. So outer radius you can give here as it 12 micrometer. Inner radius is 0. X center, y center, exactly we are making on top of that cross slot. So x center is you can give 0 and y center you can give 0. Here z minimum you can give as a thickness of feed line plus thickness of substrate plus thickness of ground. Then z maximum you can give here same as it is, thickness of feed plus thickness of substrate plus thickness of ground, and here added the thickness of particular DRE. So that purpose you can add plus thickness of the thickness you can give as a particular DRA material, thickness of DRA, just write TDRA. The jet maximum, the particular thickness also added here for the particular cylindrical dielectric resonator antenna. And the material you can select here from that silicon lossy. So it is not visible here, not shown any option the particular material. So for the silicon lossy material, go to the load from material library. In this library you can select that particular silicon lossy material. Just click on that material library, go to that and search here. In this design, the particular DRA material we are using in terahertz frequency silicon lossy. Just type here silicon. It is visible here. It will be option shown is silicon lossy and silicon loss free. So you can select the silicon lossy. Just after the selecting, just to go to the load and click on the preview. Here the particular TDRA thickness of the DRA material thickness will be asked. Just you can give value as a thickness of TDRA 5 micrometer. Thickness of DRA material is a 5. The value you can give as a 5. Just click on the OK. Just give preview and OK. So cylindrical CDRA material is added on the top of the ground material. It is visible or not?
Yes, sir, visible, sir.
Okay. So for clear visible, I change that particular material color. So for that purpose, I am going to change that material color as a blue color. So it is now clearly visible. The blue color one, CDRA, cylindrical DRA. It is okay,
Sir, in the thickness,
sir.
cross slot thickness we have not considered in minimum or maximum. We did not consider.
Except cross slot, sir.
Previous, whenever setting the value.
Already you can see, sir, the particular cross slot dimensions we are given here, sir. You can see the slot. That cross slot thickness we are not added, sir. We are designing top of that ground material layer, sir.
Okay.
That thickness will be added here, sir. Thickness of ground.
Okay, sir.
Okay, sir. It is clear.
Yes, sir.
So you can see here in the wiring view, I will show the particular design what we are designing today's session. So bottom feed line with the rectangular microstrip feed here, and the substrate layer, ground material layer, and the CDRA, and also we are designing the cross slot. What I shown the basic diagram, the cross slot, that also we are implemented here. So you can see. So you can see here the basic diagram what I shown in starting in this session. The bottom layer is the microstrip feed line. The top of the microstrip feed line we are making the substrate layer as a sky blue one. On the top of the substrate layer we are design the yellow color ground material layer. On that ground material layer we are design the cross slot. On the cross slot we are make it as it this pink color one CDRA. This I shown in before the starting the session. This the design we are implemented today's session. So in that one the DRA material color we can change, for clear visible purpose. Just to go to that, change the DRA material. So it is visible clearly all designing part for this nano terahertz device, particular antenna. So the designing part is over. Now for this designing, this particular design you can simulate. So simulation purpose, in this microstrip feed line you can give as a port excitation. For the port excitation purpose, you can after the port excitation by using of that microstrip feed line, after the selecting that port excitation, you go for the simulation. So now I will explain to the how to we can give the port excitation for that particular microstrip feed line, and how to after the port excitation, how to we can do the simulation process, and after then we can see the how to the that S11 return loss, how is it coming, and also we can see that far field results and the acceleration results, and also after then we can see that how to that by using of the graphene material on top of the DRA. After that we can see the tunability results also for that port excitation purpose. So the particular microstrip feed line we are giving to the port. So for that purpose you can select that particular microstrip feed line the width. So that purpose, for port excitation purpose, you can go to the modeling. Here the lot of option will be shown here. The curves, pick points. Here in this picks, one option will be shown here. Pick the face. So select that particular pick face. So where we are giving to that port excitation, that particular face you can select. So we are going to design microstrip feed line port excitation. So that particular microstrip feed face you can select here. So this is the sky blue color one is the substrate layer. The yellow color one is that ground material layer. and the top of that CDRO material is there. We are given the microstrip feed line as that bottom layer microstrip, that pink color one. So you can select that particular face microstrip feed line. Just to double select and double click on that particular microstrip feed line face. So it is selected. The microstrip feed line face is selected as a port excitation. So at that we are selected the particular microstrip feed line phase. So at that same place you can give the port. For that purpose, you can go to the home. In home, that in this last option, macros option will be shown here. So it is in this macros, it will be shown lot of option. Calculate, construct, file, materials, parameters, results, solver. So solver option will be there. After the selecting the solver, go to the ports. So we a particular face selecting we are making as a port excitation. So going to the solver, after solver the ports, the particular ports we can excitation purpose select the ports, and here that shown one option will be there, allow overlapping waveguide ports and calculate port excitation coefficient. So select this one, calculate port excitation coefficient. Just click on that one. So here the particular what we are selecting, that particular thickness of that microstrip field line thickness and width will be shown here. Just after this here, excitation coefficient purpose, just one option will be shown here, calculate and construct port from picked phase. Just click on the calculate. The K value is identified here. After then you can click on the construct port from picked phase. Already we picked the phase from microstrip feed line, the particular port excitation purpose. So we can construct the port at the top at that microstrip feed line. Just click on the construct port. So that we can see here the particular port we are making on design on that microstrip field line. So you can see here this is a port excitation on that microstrip field line. So after that microstrip field line port excitation, you go for simulation for this particular antenna design. So for that simulation purpose, go to the simulation block. Here lot of option will be shown here. Select the setup solver. Just click on the setup solver. The accuracy it will be shown as a minus 40 dB, and also it will be shown lot of option here, optimizer, parametric shift, special, simplified model, and apply and start. So after that port excitation, you can go to the simulation, select the simulation, just to apply and click on that start button. So it will be started here, the particular antenna design what we are design, the simulation it will be started. So the simulation it will be take 2 to 3 minutes time. Sir Nageshwara sir, it is the simulation option
Sir,
running sir. It will be take mostly 2 to 3 minutes time sir.
okay, sir. Okay. Wait.
So after that simulation, you can see the results, how we can get the results for this particular antenna design. So I will explain shown the expected results. Already I designed the same antenna design in another file. I will be show that particular result for this particular antenna. It is, you can see here this particular antenna design S11 return loss results below minus 10 dB. We are getting to good bandwidth of bands. So we can see these results are coming or not for this particular design. It is going for the simulating is going on. So we are in this design that particular values are given because of already we done this antenna design with a lot of parametric analysis. So that parametric analysis, the different values are we are simulating. So we are choosing the particular value what we are good results. The particular values we are given this today's antenna design. Already we done this antenna designing simulation with a lot of parametric analysis and optimization. So the particular values already we identify and for the good results we are achieved. So that particular values for this particular materials we can give in here after the lot of the parametric analysis and optimization techniques. So today's session also that particular dimensions values we are taken and designed and simulated now. The simulation point, the simulation also completed here. So now we can see that what the we can how much results are we are getting. We can see that going to the go to the 1D results, your port signals and S parameters, reference impedance, balance, power, energy, materials. A lot of option will be shown here. Just go to the S parameter. Here was S11. So basically in gigahertz frequency or terahertz frequency, when we are going to the design the particular antenna, you can basic thing what we are you can see that S11 results are getting or not. If you are getting the good results in S11, if you can approach the to go to the gain identification, radiation efficiency, axial ratios, electric field, magnetic field, and tunability. If you are getting that S11, all in any Gizaza research scholars or any R&D, after the simulations, after design and simulation, all the particular antenna, how much return loss the S11, how it is coming, that thing is main important. So that thing we can see now in S11. So we can see here what we are designing today's hands-on session. The particular antenna design, you can see the minus 10 dB. The three bands are allocated here. The after the simulation, we are achieved the three bands. You can see it is visible or not, sir?
Visible, sir. Clearly visible.
So you can see here. So what we are in starting 0.1 to 10 terahertz frequency we are selected. On that 10 terahertz frequency we are design this particular antenna design. With by using a microchip feed line with a aperture coupled as a cross slot. On the cross slot top of the CD array, we can design the particular dielectric resonator material. After that designing part, we simulated this particular design. After that simulation part, we are getting these results. We are getting the good results. You can see 0.1 to 10 terahertz. We are getting the three bands. You can see here at 5.5 terahertz. This is the central frequency. You can see the bandwidth also very high for this band at 5.5 terahertz, 5.14 to 5.9. So almost 1 terahertz frequency we are maintained here, that particular. So this is a very good result. I think this for this result we are getting one conference paper or any symposium also. 1 terahertz means a very good results in terahertz frequency. it is covered almost almost 1 terahertz. Okay, this is the high bandwidth of terahertz. High bandwidth of band is covered at 5 to 6 terahertz. It is visible or not?
Visible, sir.
Okay, sir. So you can see this is a particular band what we are designed. This is a very high bandwidth of band, and also you can see that another band is covered at 7.2 terahertz, and third band is covered at 8.2 terahertz. These all things are covered with high bandwidth of structure. So it is a good results. I think we are getting that by using of today's sessions. This antenna and a particular antenna by using of microstrip field line cross-slotted aperture coupled by using of the DRE with the thickness of 1.52, we are achieved good results. So this is the written loss of that particular antenna design. So now we can go for to how to see that particular antenna design we are achieved axial ratio or not. So axial ratio also, this is a very important aspect in antenna designing. So already we have achieved 3 bands in that particular antenna frequency ranges as a 5.2 5 terahertz to 8.5 terahertz. In this frequency range, we are getting very good results. 3 bands we are achieved. So axial ratio we are getting or not, we can see it at a particular 3 bands we are getting that axial ratio as matched or not. We can we can see that particular axial ratio is matched or not. If your axial ratio matching with this 3 bands, your antenna is going to that circularly polarization. In this 3 bands we are not getting any axial ratio, that our antenna goes to that linear polarization antenna. So for that circular polarized or we are getting or not, we can see by using of axial ratio results. So the axial ratio results purpose. Sir, can I explain this thing axial ratio or not? Directly I can show that how to graphene material using on top of the CDR, how to tunability we are getting, but particularly what we are getting the results. The axial ratio is taking long process, sir. Time taking process. Can I explain or go for to that graphene material?
Sir, just show where to see that one and later you can.
That axial ratio value, sir. How can we can
Where to see on